Dark matter is always a hot topic, but what if you were asked about an intriguing question? Is dark matter warm or cold? For how many times have you thought about it? Can you answer this question? It's perplexing though. It's Earthy Perks with a new episode that brings an interesting question about the temperature of the dark matter. Space is filled with an invisible mass known as dark matter, accounting for 27% of the mass and energy in the observable universe. The existence of this matter was intended to explain all the missing baryonic matter in cosmological models. Unfortunately, the concept of dark matter has solved one cosmological problem, only to create another. So far, theories have ranged from saying that it is made up of cold, warm, or hot matter, with the most widely accepted theory being the lambda cold dark matter lambda CDM model. However, according to a new warm dark matter WDM model, may be able to explain the latest observations made of the early universe. The lambda CDM model is based in part of the theory that dark matter is cold. As cosmological explanations go, it is the most simple and can account for the formation of galaxies or galaxy cluster formations. Cold dark matter has been speculated to take the form of massive compact halo objects, machos, like black holes, or a class of undiscovered heavy particles, example, weakly interacting massive particles, WIMPs, and axions. The existence of dark matter as massive particles that have low FSL would result in small fluctuations in the density of matter in the early universe. This would lead to large amounts of low-mass galaxies to be found as satellites of galactic halos, and with large concentrations of dark matter in their centers. The cold dark matter particles are characterized by low root mean square velocities due to their large masses, usually assumed of the order of greater than 100 GeV, 100 times the mass of a proton. Such low thermal velocities allow for the clumping of CDM even on very small scales. Conversely, lighter dark matter particles with masses of the order of GeV, around 1/500th the mass of the electron, would be characterized by large thermal velocities, inhibiting the clumping of DM on mass scales of dwarf galaxies. In other words, it is found that the WDM could better account for the early universe as we are seeing it today, whereas the lambda CDM model would result in perturbations in densities in the early universe. Galaxy formation is deeply affected by the nature of DM on the scale of dwarf galaxies. A powerful tool to constrain DM models is to measure the abundance of low-mass galaxies at early cosmic times, high redshifts, z equals 6 minus 8, the epoch of their formation, T. This is a challenging task since it implies finding extremely faint objects, absolute magnitudes, MUV equals -12 to -13. This should be done at very large distances, 12 to 13 billion of light years, even for the Hubble Space Telescope. For almost a century, dark matter has been a pervasive and elusive mystery, always receding away the moment think we are about to figure it out. But the deeper we look into the known universe, and the farther back in time, the more we are able to learn about its evolution. Hence revealed, the dark matter in the universe is cold. This is Earthy Perks, signing off with a promise to come up with new and exciting topics for the latest episodes. Till then, stay tuned.